Welcome back to GLS4OM. We're starting our last unit. We're done with the calculus, and now we're going to move on to some linear algebra types of things. So this unit is going to be about matrices, and it's going to teach you some of the skills you need with regard to linear algebra in case you end up taking that course at university next year. So, as keeping with our past practice, here are some two humorous comics for the day. I'll let you take a look at those. And perhaps you find them funny, perhaps you don't. Everyone always wants an island in their kitchen. And who hasn't played the game of Operation over there in the corner? All right, this lesson won't be a very long one. It's sort of looking at the history of matrices, or matrices throughout history. So the first place we're going to stop in is Babylonia. So studying the system of linear equations, and just to let you know what that means, so I have an equation x plus 2y plus 3z equals, I think I'll do equals 4. This is considered a linear equation because the exponent of all of the variables or the unknowns is 1. You could have a system of 5 equations and 5 unknowns. It's a linear system if the exponent for each of the variables is 1. So the study of linear systems and a desire to solve them eventually leads to the development of matrices and determinants. The Babylonians studied problems which led to simultaneous linear equations, which you did in grade 10. You started with 2 equations, 2 unknowns, and you learned how to solve them around 300 BC. So the problems they were looking at would lead to simultaneous linear equations. So here's an example of a problem they were looking at. There are 2 fields with a total area of 1,800 square yards. One produces grain at a rate of 2/3 per square yard, while the other produces grain at the rate of half a bushel per yard. The total yield is 1,100 bushels. What is the size of each field? So I think what we'll do now is we'll take a time to ponder pause. This is really a question you would have done in grade 10 math, and let's see if you can figure out the solution to this one for fun. Again, a time to ponder pause. Taking this up and looking at some potential solutions. First thing we would do, we have an equation based on the total size of the fields. Altogether, it was 1,800 square yards. They were measuring in square yards. So x plus y is 1,800. And then we had the other equation produced on, or based on, production. How much grain can you produce in terms of bushels? So 2/3 times x plus 1/2 times y is equal to 1,100. Similar problem you would have done in grade 10. The problems that I can think of relate to, I think it was a fair buying hot dogs and hamburgers that I can recall. So you'd have to solve this linear system. If this was grade 10, perhaps what you might do is I might multiply by 6. That's what I did. I want to clear the fractions. So if I multiply by 6, I'll get to this equation, 4x plus 3y equals 6,600. I'm not a fan of substitution because it makes you work with fractions. So I'm going to use elimination. And what I'm going to do now is I'm going to take this equation and I'm going to multiply it by -3. That will give me this equation. And now when I add, I will be able to eliminate the y variable. That will give me x is 1,200. And then back substituting into here, 1,200 plus y is 1,800. That gives me y is 600. So that's what it would have looked like in grade 10. For those of you who have seen matrices already in your calculus course, so a matrix we would set up, this is the column for the x unknown, this is the column for the y unknown, and this is the constants. So just plugging in the coefficients, and again, more on this later, so don't worry if you're not following. We'll go into more detail later. And so there is my matrix in which I'm only going to work with the coefficients. I'm going to do the same thing I did here. I'm going to multiply by 6. So when I multiply by 6, again, look at what we're working with. We're eliminating the need to carry all the variables. So this gives me 4, 3, 6,600. And then what we do is we want the pivot here to be 1. And I'm going to use this pivot to eliminate a variable, similar to what we were doing over here. But in this case, the variable I would be eliminating would be x. But I didn't do that over here. I eliminated the y. So in order to get rid of this, what I would do is multiply this row by -4, and then I would add it to this row. So -4 times that, plus 4 is 0. -4 times this, plus 3 is -1. negative 4 times 1800 plus 6600 is negative 600. So I created a new row 2 by performing this operation. And then what I'm going to do is I want the pivot to be positive 1, so I'm just going to multiply row 2 by negative 1, similar to how I multiplied that row by a negative. This would give me 0, 1, and 600. And then what I'm going to do is I would like to eliminate this, so now I will know exactly what x is. So in order to do that, I'm going to multiply row 2 by negative 1 and add it to row 1. So multiply this by negative 1 and add, I get 1. Multiply this by negative 1 and add to this, I get my 0. Multiply that by negative 1 and add it to this, I would get 1200. And so now I can see that x is 1200 and y is 600. Moving forward with the history of matrices. Now that's not how the Babylonians solved this. I know when we solved it, you would have worked solely with x and y. What the Babylonians did was they selected, I'm going to call this sort of a mean value, and they said let the mean of x and y be equal to each other, then 2x mean is equal to 1800, so x and y mean, they're both equal to each other, they're 900. And now they introduce a third variable called d. And then they say we're going to adjust x by adding d, and we'll adjust y by subtracting d. So x is equal to the middle number, which they just found to be 900, plus d, and y is the middle number, minus d. And then we plug into this equation right now, and we will replace it with 900 plus d, because again, the mean x and y are equal to each other. And in here, we're going to replace it with 900 minus d, and then we'll solve this system based on one variable, and we'll find out that d is 300. And then to find x, I add 300 to this, and to find y, I'm going to subtract 300. So they do get the same answers as we would. However, kind of an interesting technique to introduce a third variable and start at the halfway point and then move up and down from the halfway point. More history, the history of matrices in China. So the concept of matrices were first introduced in a book, 9 chapters on mathematical art written during the Han Dynasty, sometime between 200 and 100 BC. Now this was a problem they were trying to solve. There are 3 types of corn, of which 3 bundles of the first, 2 of the second, and 1 of the third make 39 measures. That would be this column right here. And then we have 2 of the first, 3 of the second, and 1 of the third make 34 measures. 1 of the first, 2 of the second, and 3 of the third make 26 measures. And how many measures of corn in 1 bundle of each type? So they're going to set their equations up in columns. We don't do that today. What you'll see is we do it in rows. And then this is what it said in their book on how to solve this. The reader was then instructed to multiply the middle column, which would be this one. Multiply the middle column by 3. So multiplying this by 3, and subtract the right column as many times as you can. So if you times this by 3, you'll get a 6. So to get that to disappear, the most you can take out is 2 times this. So you're going to do 2 times that. And so when we do this, for this particular column, we're going to do 3 times 2 minus 2 times 3. 3 times 3 minus 2 times 2. 3 times 1 minus 2 times 1. 3 times 34 minus 2 times 39. That's how we created this column. And then they want you to do the same kind of idea with this last column here. So what they want you to do is subtract the right column, which is 1 in this case, as many times as possible from 3 times the first column. Sorry, the right column is this one. So how many times, what are we going to multiply this by? I think I'll word it that way, right? In their writing, they said subtract the right column as many times as possible from 3 times the first column. 2 times 3, 3 times 2. So in this case, I'm just going to think of multiplying this column by 3 to get your 0. So 3 times 1 minus 1 times 3. 3 times 2 minus 1 times 2. 3 times 3 minus 1 times 1. 3 times 26 minus, that should say 1, I'm not sure why that says a 2, minus 1 times 39, and that will give you the numbers we're seeing here. And then you're told to take this new, which would be a new matrix, And then you're told to multiply the leftmost column by 5 and the middle column by 4, because we're going to subtract it as many times as we can. So multiply this by 5 and this by 4. That will introduce a 0 here. And so that's where all of these numbers came from. 5 times 4, 5 times 0 minus 4 times 0. 5 times this column, 4 times this column, to make that disappear. So 5 times that, and then 4 times that. 5 times that, subtract 4 times that. 5 times that, subtract 4 times that. And that will get us down to here. So now we've created another 0. And, whoops, went the wrong way. And then we'll finish off with this. This is going to give that 36z is equal to 99 based on here now, what we have left. We have 36z is equal to 99. That gives us that z is 2.75. And then we will go backwards to here. We've got 5 plus z is equal to 24, but we now know what z is. So 5y plus z is 24. That gives us y is 4.25. And then we're going to have to go to this column, which is 3x plus 2y plus z is 39. So 3x plus 2y plus z is 39. But we know what y and z are, and that gives us that x is 9.25. Very similar to Gaussian elimination that we used today. Major difference is we are using rows rather than columns, and I actually find it, because I'm so familiar with matrices, I find it difficult to follow what they were saying because I keep wanting to do my elimination row-wise rather than column-wise. So what I'm going to suggest you do now is you try to resolve this problem using matrices if you've seen them already. And again, I'm going to take a time to ponder pause. Okay. Resuming just briefly, just to make sure that you set this up. So our equations were 2x plus 2y plus z is 39. That was their leftmost column, but it will become one of our rows. The next equation was 2x plus, that should say 3y, plus z is 34. And then the last column was x plus 2y plus 3z is 26. And now if you've worked with matrices before, we would like a pivot to be 1. So if I write this row first, it really doesn't matter in which order you write these, but I'm going to write this row first so my pivot is already 1. And then I chose to write this row and then that row. So if you already know how to row reduce on matrices, why don't you practice that now? If you don't, I'll walk you through the process, but we will have a formal lesson on this later. Again, a time to ponder pause. All right, so resuming to take a look at this. I am now going to use this pivot here to eliminate the x components here. So if I multiply row 1 by -2 and I add it to row 2, I will eliminate or make this 0. So -2 times 1 plus 2 gives me that. -2 times 2 plus 3 gives me that. -2 times 3 plus 1 gives me that. -2 times 26 plus 34 gives me -18. Now I'm going to do the same thing over here. So what I will do is I will replace row 3 by multiplying row 1 by -3 and then adding it to row 3. So -3 times 1 plus 3 gives me 0. -3 times 2 plus 2 gives me -4. -3 times 3 plus 1 gives me -8. -3 times 26 plus 39 gives me -39. And now we want this one here to be our next pivot. I do not like my pivots to be negative. So what I'm going to do over here is create a new row 2 by multiplying the old row 2 by -1. So I will get 0, +1, +5, +18. That's how we got to there. And now I'm going to use this as a pivot to zero out these two components here. So for row 2, it will be -2 row 2 plus row 1. And for row 3, it will be +4 times row 2 plus row 3. So I'll walk you through that now. So we're going to multiply row 2 by -2. So 0 times -2 plus 1 gives me that. 1 times -2 plus 2 gives me that. 5 times -2 plus 3 gives me this. 18 times -2 plus 26 will give you this. And then we'll repeat what we're going to do for row 3. And again, I need to multiply this by 4 and add to zero that out. So we do 0 times 4 plus 0, we get that. 1 times 4 plus negative 4 gives me that. 4 times 5 plus that gives me that. 18 times 4 plus that gives me that. And now our new pivot, I mean, I suppose at this time, if we don't want to continue, we now know that 12z is 33. But I'm going to just keep showing you how to pivot off this column and make these guys 0. So what I'm going to do now is divide by 12 because I want my pivot to be 1. So row 3 is equal to row 3 divided by 12. Divide that by 12, get 0. That by 12, get 0. That by 12, you get 1. 33 divided by 12 gives us 2.75. And so now continuing this pivot process, this is now the new pivot. So in order to clear this in row 2, it will be row 2 equals negative 5 times row 3 plus row 2. And to clear this one out, I'm going to need to do 7 times row 3 plus row 1 in order to clear this out for row 1. So let's start with the row 1 first. So 0 times 7 plus 1 is 1. 0 times 0 times 7 plus 0 is 0. 1 times 7 plus negative 7 is 0. 2.75 times 7 plus negative 10 is 9.25. And to zero this one out, we were going to multiply by 5. So 0 times 5 plus 0 is 0. 0 times 0 plus 1 is 1. 1, oops, sorry, we're doing negative 5. Let me repeat that because it has to be the opposite sign. So 0 times negative 5 plus 0 is still 0. 0 times negative 5 plus 1 is still 0. 1 times negative 5 is negative 5 plus 5 is 0. And now 2.75 times negative 5 plus 18 will give us 4.25. And now reading our solutions across, we now know that this is x. And remember, that was x, that was y, and this was z. And we're going to cross that off. So I now know that I have one x, and these are zeroed out. So x is equal to 9.25. There's no x, there's no z, so y is equal to 4.25. There is no x and there is no y in this row, so z is equal to 2.75. So that's how the row reduction in matrices, this one's called the Gauss-Jordan method. Again, don't panic if you weren't following, more on that later. Very similar to what the Chinese were doing over here. They're eliminating based on columns, we eliminate based on rows. All right, where to next? Saiki, Takakazu, and Leibniz developed the idea of a determinant, both around 1683. Saiki published general methods for calculating the determinants of 2 by 2, 3 by 3, 4 by 4, and 5 by 5 matrices. The greater the order of the matrix, the more difficult it is to find a determinant. It's very simple to find a determinant of a 2 by 2. You then have to split into 2 by 2s to do a 3 by 3. And then a 4 by 4, you'd have to split into 3 by 3s and 2 by 2s. So it becomes more complicated. Leibniz proved a precursor of Cramer's rule, and he expanded determinants along columns. That later was known as Laplace expansion. You're likely to be exposed to that in university. In the 1730s, Colin Maclaurin wrote proofs of Cramer's rules for 2 by 2 and 3 by 3 systems. And in 1750, Gabriel Cramer developed the general rule for an n by n system. And I think I skipped one. We were here. I forgot to do this one. So let's back up to 1545. Gerolamo Cardano, he published this booklet here, and he outlined a method for solving a system of 2 linear equations. That's not too hard. I mean, you know how to do that. You did that in grade 10. His rules led to the formula below, which you could later manipulate into Cramer's rule. So what I'm going to suggest you try right now is set this up as a matrix and see if you can, if you were able to follow what we did here. Pivot 1, 0 out below it, pivot 1, and then 0 this out because this is a 2 by 2 matrix. See if you can 0 it out and check what you get for x1 and see if that is going to be equal to that. And again, we'll do a time to ponder pause. All right, so resuming, I'm not going to go through this in great detail because some of you might not have done row reduction on matrices before. But initially we will set up with our coefficients A11, A12, constant B1. Coefficients A21, A22, constant B2. I need to make my pivot 1. I did that by dividing everything by A11. In order to zero this out, I'm going to need to multiply this row by negative A21 and then add it to that. So multiply by negative A21, add to that. Multiply by negative A21 and then add to that. Here I simply got a common denominator. That times that plus this times this all over A11. Same here, common denominator, multiply that by A11. The whole thing over A11 will get you to there. And now the next thing is I need this pivot to be 1, so I'm going to divide by this. When I divide by this piece, this will be 0, this will become 1. Invert and multiply, the A11s will go, and we will get to here. And now there would be one step left. What I'm going to need to do is multiply this row by negative this, so that when I add, they go. So multiply this by negative A12, A11, and add. Multiply this by negative A12, A11, and then add to that, which is exactly what I've done here. So the only change was made to this row, zeroing it out. And of course, if you multiply this by negative A12 over A11, you'll get 0 plus 1 is still 1. Negative A12 over A11 plus A12 over A11 becomes 0. Now, a negative A12 times A11 times this plus that gave me this expression right here. And I now can see what x2 is equal to. x2 is equal to this. x1 is equal to this. And then I will leave it up to you to show that it really is the exact same as that. You probably want to get a common denominator here and get a common denominator there and simplify. And then a common denominator here to clean this up. And you'll see that those two are one and the same. All right, so out of order, I already covered that slide. We were just talking about Colin Maclaurin, who wrote proofs of Cramer's rules for 2x2 and 3x3. And we saw Colin's work on last unit when we were looking at Maclaurin polynomials that are centered at a equals 0 and how they were useful in integrating when there isn't an explicit formula for integration. This is Gabriel Cramer over here, and he developed the general rule for an n by n system. Then we come to Gauss. Carl Friedrich Gauss introduced the term determinant in 1801. He described operations. He described how to multiply matrices, which we're going to learn. The inverse of a matrix, he did that as well. We'll learn how to do that. He was studying the orbit of the asteroid Pallas, and he obtained a system of 6 equations and 6 unknowns. That's a lot of work. So he developed the method Gaussian elimination that I was trying to show you earlier for solving using the coefficient matrix. So the coefficient matrix that we had written here. So constants were here, coefficients were here, saves you all the laborious effort of continuing to write all of the variables. What was the next major development after Gauss? Turns out that James Joseph Sylvester coined the term matrix. It's kind of an odd word. Why matrix? It actually comes from the Latin word for womb. And this is why he chose that. I have in previous papers defined a matrix as a rectangular array of terms, which indeed is what it is, out of which systems of determinants may be engendered, as from the womb of a common parent. That was his inspiration for calling these rectangular arrays of terms matrices. And we still use that term today. Then Arthur Cayley created the first abstract definition of a matrix in his memoir, The Theory of Matrices. He did that in 1858. This establishes it as a valid and viable branch of mathematics. He defined more operations. So Gauss did multiplication, but Cayley is doing, he's defined addition, subtraction, scalar multiplication. He also talked about inverses and multiplication as well, but Gauss did those first. So this cements this into a viable topic in math. Next contribution. So this is Wilhelm Jordan. He described a method which extended Gauss's. Now in Gauss's method, Gauss was doing this: pivot, 0, 0, pivot, 0, and then make this a 1. And he didn't necessarily even want that to be 1, but he didn't, Gauss was not concerned about zeroing these ones out. He sort of found those out by back substitution. It was Jordan who said that what we're going to do is make the pivot 1, everything else 0. Next pivot 1, everything else in that column 0. next pivot 1, everything else in that column 0. So this was Jordan's addition to Gauss's method. So that method is now known as Gauss-Jordan elimination, and this is called a reduced echelon form matrix right here. He developed that in 1887, and as I mentioned, that's known as Gauss-Jordan elimination. Last major contribution, Leon Mirsky. He wrote a famous text. It's called An Introduction to Linear Algebra in 1955, and that cemented matrices as an important undergraduate topic in mathematics. So some of you heading off to university will be taking calculus, but some of you are going to be taking linear algebra, which is really looking at matrices and the solutions of linear systems. And we can thank Leon Mirsky now, because it was this book that ensured that that would be taught as in undergraduate first year courses in which you need math, maybe engineering math, stats, etc. All right, so that brings us to the end of this lesson, which was sort of a history of matrices. Further lessons, we're going to look at operations. In fact, the next lesson, we're going to be looking at Gaussian elimination. So if you couldn't follow it here, don't panic. We have a whole lesson devoted to that. If you made it to the end of this video, once again, thank you for watching. Don't forget to like and subscribe. And as always, take care and stay safe.